we will see natural transformation as an end. Now, what is this strange beast? I will talk about it and maybe show some little bit of Haskell in the end. Let's go back to the original definition, where we had natural transformation alpha defined as a family of morphism in D, indexed by the object of C, such that for any morphism F in C, the corresponding square would commute. It's a very strong and very specific condition. And you can see that this definition is internal. That is, we are drawing things inside of the category C and D. We're really looking at what's going on inside. Now, it's very often beneficial to take an external point of view. That is, and there's one very, very stupid way to do that. Alpha x, when we draw that as an arrow inside of D, we can say, okay, alpha x is just a member of this set, D f of x, g of x. And being a member of that set means we can draw this diagram in set from the very specific object 1, which has just one element inside of this set. And picking alpha as a morphism in D is really just drawing an arrow from this one element set. We have an equivalence between the two. And we have here an external point of view. We don't look what goes on inside of D. We just have this functor D, F, G, and we are instantiating it at X, and we have a drawing in set here. So can this be the basis for extending all the concepts that we have here and make them external? So let's draw all the pieces we have. And we have this diagram in D. Now we have alpha x, alpha y in set as arrow from 1 to the two sets here. And what are the two arrows which are left? Well, one is a postcomposition, and you can see that if you start from alpha x, in our condition we postcompose by g of f, and the other one is precomposition. We start with alpha y and we precompose by f of f. So this describes faithfully the square that we have drawn internally in D, but it's completely external. And the condition that we require is that this square in D commutes. And this condition corresponds exactly to the commutation of this diagram in set. Now, we have expressed our internal condition as an external condition. Let's look a bit into what this functor is. D f underscore g underscore. It goes from C up cross C to set. And so for PQ, it will map to the set of morphism from FP to GQ. And if we have a paramorphism in C, so that is one morphism in the cross, the Cartesian product C up cross C, it will act by precomposition and postcomposition. And the way we can see that internally, because it's easy to see internally, is we take any morphism from FP to GQ, we precompose it by f of f, and we postcompose it by g of g, and it gives us a morphism from FR to GS. So we have indeed a function. The action of this functor on morphism from the Cartesian product will be mapped into functions, and the function takes a morphism from this set DFPGQ, and it will map into an element of this rival set, the target set, DFRGS. And this is indeed what we have built. We have a function because we're in set. So with those definitions, we have our natural transformation expressed as a family of a morphism from 1 to df to the application, if you want, of this functor to xx, to the diagonal in a way of C. And the fact that this commutes, the condition of commuting in set for any morphism f in C, is what is the definition of a wedge. it's a very specific family of morphism, because it says basically you can post-compose or pre-compose, and it will commute. And it's a wedge of summit 1. Now we're happy, we have some external definition, we have this notion of a wedge. And this notion of family, which permutes in a way for all f in C in this diagram. So this is a very important point. It's the same family. The family is indexed by the object of C, and the commutation happens for all f. We have a fixed family which is quantified over all f. And so you have the guarantee that this diagram will commute for any f that you can pick. Now we're happy, but can we put something more in this shape? For instance, we have this set nat fg, the set of natural transformation from f to g. Could it be that we can draw some family of morphism, tau x, tau y, so they would be functions? Could it be that we have such a family and that it would commute? Well, if we think about the kind of function that it would be, it would take some natural transformation alpha and map it to some element from f of x to g of x, f of y to g of y, etc. Now, what's the natural way to do so? Well, if I have alpha, I can apply it in a way, look at its morphism at index x. And of course, I will have this commutation property, because that's what defines a natural transformation. So those morphisms tau x, tau y are very specific morphism. They're a morphism that takes any natural transformation and apply it at the component x, which is part of the definition of, which is part of what is given to us in a natural transformation. And the commutation arises from the naturality property. And not only is it, so it's a wedge, because this is valid for any f, but it's like the biggest wedge for this functor, df underscore g underscore. Because for all natural transformation, you have a arrow from 1 to nat of f, and conversely, if you give yourself an arrow from 1 to nat f of g, you have indeed a natural transformation. So all sides of this diagram commutes. So to sum up, a natural transformation is a wedge from 1 for this functor, and the set of all natural transformations is the biggest wedge for this functor. And if you want to know more about this end and coend, which I encourage you to do, is you can look at this paper. This is a coend, My Only Co-Friend, by Fosco-Lorraine. It's a really good paper, and it's very useful for CAN extension, Yoneda, etc., etc. And as a final bonus, you can, those things are a nice concept, but we can actually program it in a way, and that's of course what Mr. Kmet is doing. So in Haskell, you would say an end. If I have a witness of this type, end, that means I can destruct it, and I get a value of that type, and that means for all A, those would be the objects of my category. I have a witness of PAA. Of course, it doesn't have, unfortunately, the commutation property. It's kind of informal in here, and this P is really just a Hom set. It would be this D F underscore G underscore. And all this is absolutely not explicit. It should be enriched, but you can see that all those concepts, they translate in code directly, and we can show various kind of isomorphisms also in code. that concludes this fourth way, I guess, of seeing natural transformation.